Good morning, everyone. And as you will see, I am an outlier here. You speak about numbers and money and market to time from our discovery to market. Here we are dreamers at CERN. We dream and then we say, oh, this could be possible, and then we just go and do it. So please pardon my quality of transparency slides as well, because these are not coming, from the industrial standards. All right, so I'm coming from CERN, and of course, this is a privilege to have been working there for nearly 40 years now. So, and to have seen the growth from an idea into the R&D, into building prototypes, building large experiments, and then looking at those data as well, coming from those large experiments. And once in a lifetime opportunity, what are the chances that you get to see a Nobel Prize coming from your work? So it's been an incredible journey, and I'll just share with you a little bit of the excitement and a little bit of the process of how this goes into looking for very big questions. And of course, CERN is in Geneva, Switzerland. So we are from Switzerland. The previous speaker was from Zurich, and here we are, somehow, tiny country in Europe, and two speakers here, great country. So yes, what do we do at CERN really is to understand the forces and the particles in the universe. Where did we come from and where are we going? The typical question. And for that, I should also say that we have built this mega structure of an accelerator, which is actually a system of accelerators that started in the 50s. So it's not just one large hadron collider that you may have heard of, but it is a system of accelerators built one on top of the other, so that, from the small to the bigger, it keeps feeding to the point where we have this very large hadron collider. And of course, it's not done without people. We are 17,000 people working at CERN. Not everyone at CERN, of course. We are about 3,000 people employed by CERN, and the others are coming from all over the world, including the UK. And our next Director General is coming from the UK, Mark Thompson. You may have heard about him as well. So, 4 pillars underpin CERN's mission. One is, of course, research. That's the basic research in particle physics. We look at the open questions for the universe, and we can't do that without collaboration. It's completely technology-driven. So we have a facility at CERN that we offer to scientists who come with their questions, and they try to do experiments. At CERN, it's very open. It is a European laboratory, but you come with your ideas, and if you can pass through the thresholds of all the reviews and committees, you are able to proceed. If you come with the money, of course, then you can do your experiments there. And the vision of the management is incredible. There are questions that have been asked or formulated in theory in the 60s, and then, as all of you know, the Higgs boson was discovered in 2012. So the confidence and the belief that we will be able to find the technology to discover the Higgs boson 30 years down the line is what is completely incredible, and something that I learned on my way as we went along. And clearly, there's a lot of education and training that comes along, without which we can't be, continuing this intergenerational experiment. When I came in at CERN in 1987, I was just a little student, as you can imagine. And then there were people designing these big experiments, these very large experiments, and I could not understand a single word then. Not that I understand much now, but the belief that the next generation is going to carry the knowledge and the competence to be able to build, upgrade, maintain, operate, and then analyze the data coming from these very large experiments. And these experiments are, of course, it would take me another talk to explain all the kind of different sensors that are in these large experiments around the Large Hadron Collider, because we are colliding protons and somewhat recreating the Big Bang. and obviously not making black holes and gobbling up the earth and so on, as we hear in the news. But what we do is that in a very safe environment, we recreate the conditions that were there in the universe 13.8 billion years ago. Just a few minutes later, because we can't get there. We don't have enough money to have enough of those, the energy that's needed to come there with our accelerators. So yes, open questions about matter, about the mass given by the Higgs boson, antimatter, dark energy, and of course gravity. These are the open questions that we are looking at. And clearly, physicists are not very creative. They don't have fancy names. So whatever we don't understand, we just call it dark. Everything is dark, so we don't understand that, right? So indeed, technology goes hand in hand. From the very beginning, CERN has had an edge in these three sectors of technology. Accelerators, clearly, we are with superconducting accelerators that operate at minus 271 degree, and detectors that have hundreds of millions of channels, and they detect particles at the rate of 40 million times a second. That's the rate of collisions in the accelerator. And then computing that sifts the data that comes out. Each single collision of those 40 million times a second is of the order, the data is of the order of 200 gigabytes. So we have to sift, take away what we don't need, and out of those 40 million, we have to keep only 100 events of interest, because physics, which is discovery physics, is very, very improbable. So 1 in 10 to the 14 events is what we are interested in. So sifting the data and the speed at which we need to sift the data is the connection I understood a little bit with what you all are doing, which means this error corrections and the feedback loop of the error corrections. So yeah, I mean, these activities are very, very important. My personal activity has been on the detectors, radiation detectors, building, researching, etc. So yeah, all of you are invited to come to CERN, by the way. So please do come in the winter, if possible, because then we can go down, because we have maintenance during that time. And when we go down, we can actually not really walk around the 27 kilometers, but at least a little bit of it. And I can show you the accelerator, which has been one of the incredible achievements of humankind, I would say. So these are 100 meters underground, sitting on a very strong granite plate of the earth so that it's stable. And each, how many? We have more than 1,232 big magnets and then small corrector magnets and so on. So enormous infrastructure handled all by, very senior engineers, and then up to the last student doing the quality control of every interconnect. So yeah, these detectors, we actually are very open in the sense that whatever I'm saying here, you can feel free to go and repeat anywhere. So the collaborations are worldwide collaborations. Initially, CERN is a European organization. It's Centre Européen pour la Recherche Nucléaire. However, from the time that we need more money, more people, and of course we have to collaborate as well. So we have become now a world laboratory, which is the World Laboratory for Particle Physics. And many experiments go on, not only the Large Hadron Collider. So here we have, as I mentioned earlier, the detectors that measure the collisions, because the energy of the collisions can be converted into new particles or into energy itself or photons, or just, we need to make sure that we completely grab everything that's coming out from the collisions so that nothing is lost or nothing is missing. I mean, you all know the famous E is equal to mc squared, obviously. So all this data is what we are looking at. And the worldwide LHC computing grid stores the data, it distributes data and processes, analyzes, and then we have 170 data centers in more than 70 countries. So 1,500 petabytes of CERN data is stored worldwide, and a student in Sri Lanka can be doing his or her analysis on the data, and within 15 minutes, the data is accessible. So this is incredible collaboration. And I mean, I can only be proud that I'm part of this big collaboration that on the 4th of July, 2012, we had our Director General very excitedly telling the world, I think we have it. And that was the Higgs boson, announced by Fabiola, who is now the Director General, and Joan Candela, who was the spokesperson of my experiment, the compact muon solenoid experiment. And of course, the Nobel Prize was given for the Higgs boson to Peter Higgs at Edinburgh and Francois Engler in Belgium. So yes, how do we do that? You know, what is the direction? What is the next step? So we are driven by something called the European Strategy for Particle Physics. And there, physicists from all countries get together every 5 years to update the strategy, nevertheless setting a direction and then ensuring that we are moving in that direction. So as you can already see, that we've got now this little Large Hadron Collider, and the future is 100 kilometers, 90 miles or something, future circular collider. That's what we are looking at to look for new physics, like we said about dark matter and so on, and many, many other theories that are going around. So speaking of the collaboration and how this came together, in 1954, with 12 European member states, just after the World War, scientists picked up the scientists in Europe, and this collaboration started, supported by UNESCO. So it's a good equivalence on the way the quantum world has been sort of following our footsteps, I would say. So yes, it is a global scientific collaboration, 25 member states, 3 associate member states, and so on. I won't go in the detail, but just to say that the whole world is together when you come at CERN. And the annual budget is 1.2 billion. That's like a European medium-sized universities, and many, many students and people, they work at CERN. So in the technology area, CERN has been a driver of innovation because as we saw that when in 1984, the Large Hadron Collider was approved, we did not yet know which were the technologies, which were the cables that will be used to be able to carry the current of 20,000 amperes at that point of time, which superconducting technology will be used. So this direction of driving innovation with the industry, so that is another important point, that there was industry working hand in hand. And today as well, we have industry working hand in hand with us to look for solutions that are needed for our experiments. And then we are not looking at creating the World Wide Web. We were not looking for that. And WWW was created at CERN. And we were, how can I say, innocent enough, naive enough to not patent that otherwise we would have had all the money to do the FCC. But it's all right. There are many, many more examples of what has come out from CERN. It's another talk, and I would love to give it another time. But medical imaging, cancer therapy, material sciences, cultural heritage, aerospace, automotive. You know, Volvo and Mercedes, they are working together with CERN to look at the autocorrection for driverless cars. So there are many, many applications in healthcare, in safety, and industrial processes as well. So yeah, I mean, just very quickly, I will flash the decision-making structures at CERN. So CERN Council is a supreme decision-making authority, and they determine the policy, which is the scientific, technical, and administrative policies. And every member state has a representative in the council. And then here is where all the activities that are going on at CERN are approved or not. And then the strategy is also driven by the CERN Council. Then there's, of course, the medium-term plan, the budget, financial statements, each country has to come and report on the spending and the contributions, because there are also in-kind contributions as well. So as you can imagine, that there are rules given down by the council, and then of course there is a president as well at the council who then looks after the whole functioning of the management at CERN. Sorry for the quality of the slide. For some reason, something has gone out here. So as you see, the CERN's executive organization is the legal representative of CERN, which manages the laboratory. This is the Director General, essentially. And Fabiola is the first lady. She also is the first unique lady Director General, take away the lady, who has had 2 terms. So for the last 10 years, she's been the Director General, and now Mark Thompson is going to take over from next January. So I think I'll skip this slide. It's a bit too detailed. I can answer questions on that. Same thing for this experiment. I mean, it's an organization that works very well. Each of the sensors, let's put it this way, or each of the systems inside the large experiments needs its own structure. So my experiment, for example, the one that I conceived and did within the large detector had 20 countries and 300 scientists. So that needed a structure of its own. So we have a project manager, technical coordinator, finance manager, resource manager, and then, of course, electronics and software and physics and so on. So all that is very, very important. And then they all talk to each other. And then when they talk to each other, obviously, they have to then synchronize with the other detectors also, so that we are in time and so on. So yes, this is great. I mean, I learned about this recently because I do not work in the OQI. So OQI is the Open Quantum Initiative at CERN. It's great. It sprung out from JESDA. And I really admire at how Switzerland's think tanks come up with these kind of ideas. And JESDA is Geneva Science Diplomacy Anticipator, which was formed, I think, almost 7, 8 years ago, if I remember. And they came up with this idea at CERN to bring people together, like-minded people together, to set up an open quantum institute on the lines of how CERN was born. Though CERN has reluctance to come forward, I'll tell you, because of lack of resources. It's not our mission. Our mission is particle physics. Now, we can't stop that and do something else. But we are happy to partner and collaborate. And this is where the QTI was then, somehow installed at CERN, which is now growing fast as well. And we are trying to see how CERN's expertise can contribute to the work and the initiative that's going on all over the world. So we are trying to see how discovery in physics can be enhanced by the quantum machine learning. And of course, we are looking at anomaly detection techniques to go beyond the standard model frontier. So that's what is really driving why would we be interested in what we want to do here, right? And here, as you can see, how can we detect the hints of new physics? And 24 qubits QML is 14 times better than the classical model. So this has been demonstrated by our colleagues, and this is where the quantum entanglement comes in. And Sophia here is sorry for the quality, something's gone wrong here. She is leading this activity at CERN, and I'm sure that, Carmen, you are in touch with her, surely. And look here, we see some people whom you recognize. And I'm really proud to say that New Quantum has now a collaboration with CERN to adopt the White Rabbit timing technology to enable data center scale quantum computing networks. So this is great, I would say, and welcome to the club, and welcome to groundbreaking work, groundbreaking discoveries, and also something that we can all be very proud of eventually. Thank you very much.
Thank you, Archana. Any questions?
Don't ask hard questions.
Okay. Yeah.
Details on White Rabbit later today?
I'm not sure. Perhaps in one of the presentations, but yes, one. Yes. Any other questions?
And I can put you in touch with.
Archana, thank you. I just want to make actually a comment. It's not a question. That the power of the networks were not mentioned explicitly in your presentation, but that's what gets the data to all the country members. And I think given that this is a quantum computing and networking initiative, I just wanted to say that how classical networks have helped CERN get the data out to all the physicists.
And we are grateful for the way the networking has evolved exponentially. Thank you.